Hello everyone. In this example, we are asked to solve this trigonometric equation. We are told that cosine of 2 theta minus cosine squared of theta equals 0, and we need to find all the values of theta that make this true. And so one thing we need to recognize right away is that the cosine functions we have involved in our equation do not have the same arguments, periods, or inputs. And that's what really is kind of adding this layer of difficulty to this question. So our general strategy when we encounter a trigonometric equation involving different trig functions with different inputs, like different multiples of theta, we're going to use our trig identities or formulas to rewrite the expressions involved in that equation until we write them all using functions of the same argument or the same multiple of theta. And so that's what we're going to do here. We're going to have to rewrite cosine of 2 theta or cosine squared of theta in terms of the other. And if we look at some of our identities here, in particular this double angle formula for our cosine function, we see that it's going to be a little bit easier to rewrite cosine squared of theta in terms of just theta using one of these 3 versions of our double angle cosine formula. By making that substitution, we'll get rid of that issue of having trig functions with different arguments or inputs or periods involved. And so the next question is, well, which version of our double angle formula for cosine should we use? And for that, we want to refer to the rest of the equation that we have to solve. Notice in the rest of our equation, the only other function that shows up is a cosine squared function. And so I think that means it'd be a good idea to replace cosine of 2 theta also in terms of cosine squared. If we wrote it in terms of sine squared or both cosine squared and sine squared, it might make solving the equation a little bit more difficult. Maybe if we write it in terms of just cosine squared and cosines, we'll end up with like a quadratic equation in terms of cosine, which isn't too hard to solve. All right, so our first step is just making a substitution here, replacing cosine of 2 theta with the quantity 2 cosine squared of just theta minus 1. We can't forget that we still have to subtract away that second cosine squared of theta and that all of this is equal to 0. So now, what we can see is we can combine some like terms. We have 2 cosine squareds and we're taking 1 away. That'll leave us with a single cosine squared of theta. We still have that negative 1 on the left-hand side. And all that is equal to 0. And so from here, I think the easiest way to solve it is to get cosine squared by itself by adding 1 to each side, and then take the square root of each side. So taking the square root of the left-hand side gives us just cosine of theta, and the square root of the right-hand side gives us plus or minus 1. Remember, when we're introducing that square root when solving the equation, we have to introduce the plus or the minus. And so now we could solve this using our general procedure and our cosine inverse function, or we could just think back to our unit circle. So remember, cosine is representing the x coordinates on our unit circle. So when is cosine of theta equal to positive 1 or negative 1? That's where on our unit circle do we have angles corresponding to these points with x coordinates of positive 1 and negative 1. And we know that first one's at 0, then we have another one at pi, then 2 pi, 3 pi, 4 pi, and so on. And we can also do this for negative pi, negative 2 pi, negative 3 pi, and so on. So we actually see very quickly that all the angles theta that are going to satisfy this equation are just those angles theta that are integer multiples of pi. And so our solution that describes all the infinitely many solutions to our original trigonometric equation are the set of theta values where theta is just n times pi, where n is some integer or whole number. So we're just getting all those whole number multiples of pi, both positive and negative.